the definite integral, and it's defined in this way right here. And oh, oops, I forgot to. This should be a summation. Oops. So you're summing from 1 to n of this quantity right here, and the delta x's are b minus a over n. This is not this. This is like a more specific version. There's a more general version where these can be anything, but just to make things simpler, we use this right here for now. And the xi's are given by these. So just to give you an idea of what's going on here, let me draw a little picture here. So you have like a function right here, right? Let's say that's a function. And then let's say this, it goes from A to B. Now, x0, so if you look at this formula here, x sub 0, that's going to be a plus 0 times delta x. So that's just going to be a. So x0 is going to be right here. And then x1 will be right here, x2 will be there. Xn will be a plus I times, or the times plus n times delta x. But delta x is this, so it's going to be a plus n times b minus a over n. And so the n's are going to reduce, the a's are going to reduce, and you're just going to end up with b. So xn is b. So 0, 1, 2, and all the way up to n. And these are equally divided out among the whole interval. Okay, so that's how these points are defined. And basically, you choose an arbitrary point in this interval. It could be one of the endpoints, or it could be an interior point between x0 and x1. That will be x1 star. Well, this is an arbitrary point chosen inside here. So these xi stars are just arbitrary points chosen in here. It could be endpoint. Okay, so that should be that could be x2 right there. X3 could be right here. Star, x3 star. Okay, and at that point, you're gonna like find the corresponding rectangle, okay? And find that and use its area. Oops. Okay. So that's just a rough idea of what's going on. And you're gonna sum all those up, and you take the limit. The limit is n goes to infinity. So what's happening is n goes to infinity. There becomes more and more of these little subintervals, and they get smaller and smaller and smaller. And when they get smaller, what's going to tend to happen, if you have a continuous function, then they're going to zero in on one point. And that's going to give you, that actually is going to be a limit. Okay, there's just going to get box you into just one thing. F is integrable if this limit exists. Sometimes this doesn't exist. We can construct functions where this just doesn't, this just falls apart. I won't get into that though. But for continuous functions, it's going to work. And for functions that have a finite number of discontinuities, it's also going to work. Finite number of jump discontinuities, because if it's other kind of discontinuities, then it might not work. Okay, so anyways, if f is integrable on AB, then the integral is equal to this limit. That's basically kind of circular reasoning right there. It's integrable if this happens, and so on. Okay, so I should say this goes to infinity. Whoa, lots of mistakes. Lots of mistakes in my typing. I should have checked this better. Okay, so let's get into like doing some exercises from the homework. And it's going to look a lot like last section where we did the left and right sums and midpoint sums, because those are examples of Riemann sums. This sum right here is called the Riemann sum. Maybe I should make a note of that. Okay, this is a Riemann sum. Okay, I'm sorry, what this means, okay, so I was just a bit confused here. What this means is here you're choosing, this is also a Riemann sum. These are different though. This one's just choosing an arbitrary point. This one is choosing the right endpoint. Okay, this is the right endpoint. So in the notation from last section, it's R sub n, capital R sub n, is what this one is. So if it's integrable, then the integral is just going to be this limit. Okay. So we'll just get some specific examples here. Number one, f of x is 2 cosine x, and x is between 0 and 3 pi over 4. In case you can't read that too well, then that's 2 cosine x is what the function is. Evaluate the Riemann sum with n equals 6, taking the sample points to be left endpoints. Okay, so now they're back. This is just really like what we did last time. So, and if n is 6, then delta x will be, okay, that's b minus a over n. So that's going to be, b is 3 pi over 4 and a is 0. So that's going to be 3 pi over 4 minus 0 all over 6, which is going to be pi over 8. Okay, so delta x is pi over 8. There's a 3's cancel, and we have a 2 down here, and we have a 4. 4 times 2 is 8. There we go. So for this left Riemann sum, let's see. Let's choose a picture first. It looks like here using the left endpoint for that one, for this one, use left endpoint. For this end, it's left endpoint. It's just nothing. For this one, it's the left endpoint. Okay. So this is it right here. This is the one. This one right here. This is the correct answer. Here, this is the right endpoint. Here, this is the left endpoint here, but then it's just, no wait, it's like, oh, it's something weird here. It goes all the way down to there. That's weird. This is like, blah. And here, it's right endpoints. Okay. And this one goes all the way down here as well. And it's right endpoint, so that's bad. And then this is right endpoint, so that's bad too. Okay. So it's this one here. And the Riemann sum is going to be, okay, so we're looking at this right here, I equals 1 to 6 of f of x I minus 1, because that's how I'm taking the left endpoint times delta x. Okay, so and delta x is pi over 8, so I'm going to put that there. And then for on a 1, it's going to be 2 cosine of 0, so that's the left. And then the next, so this first one, 0, plus, and then 2 cosine of pi over 8, plus 2 cosine of pi over 4, plus 2 cosine of pi over 4, 3 pi over 8, plus 2 cosine of pi over 2, plus 2 cosine of 5 pi over 8. Okay, and I calculated that on I just used a calculator. Okay, I just used a calculator, and all that turned out to be approximately 2.066372. Okay. And if that doesn't work, you can let me know. Okay. And then this Riemann sum represents the net area of the rectangles with respect to the x-axis. Okay, so what they mean by net area is, one thing that they mean by that is it's going to be these minus this. So these areas minus that area. So if it's under the x-axis, then it counts as negative area. If it's above the x-axis, then it counts as positive area. So net area means you're going to take the positive areas, the ones that are the rectangles above the x-axis, and subtract the negative areas from them, which are the ones under the x-axis. Okay, number 2, going right along. The table gives the values of a function obtained from an experiment. Use the table estimating the integral from 0 to 3, from 3 to 9, I'm sorry, of f(x) dx using 3 equal subintervals and a right Riemann sum. Right Riemann sum, left Riemann sum, and midpoint Riemann sum. Okay, so we have a interval from 3 to 9, and we're going to do 3 equal subintervals. So that means n is 3. That means our delta x is going to be 9 minus 3. So that's b minus a all over n. So what is that? That's 2. Okay, 9 minus 3 is 6. 6 divided by 3 is 2. So our delta x is going to be 2. So we start with 3, then we go up by 2 to 5, then we go up by 2 to 7, and then 2 to 9. And that's 3 and different subintervals. Okay, for the first one, part A, we're using right endpoints. Okay, so let me do this in green. So we're using this one. For this interval, we're using, wait, no, I'm sorry. Right endpoints. Okay, this is the right, that's the left. Okay, for this interval, we're using this point. For this interval, we're using that point. And for this interval, we're using this point. And so the Riemann sum is going to be the delta x times the sum of the 3 values. So f of 5 plus f of 7 plus f of 9. Okay, and so that's going to be f of 5 is negative 0.5. F of 7 is 0.9. And f of 9 is 1.7. And so this turns out to be equal to 4.2 when you calculate it all out. So 4.2 right there. And you'll notice that, before I answer this question, let me do the left ones, and hopefully there'll be some contrast here. So part B. So here we're using left endpoints. Okay, so that means we're using this point, and this point. Okay, so L3 is going to be 2, which is again is your delta x still, and then you're going to f of 3 plus f of 5 plus f of 7. Okay, so f of 3 is negative 3.5, and f of 5 is 0.5, or negative 0.5, and then f of 7 is 0.9. Okay, and this actually turns out to be negative 6.2. Okay, so negative 6.2 for that one. Now, these are both supposed to be approximating the area under the curve, right? Or the net area. But they're off by quite a bit. Excuse me. This is positive 4.2. This is negative 6.2. So there's a big difference between them. And if you look at these values, you can see that they're decreasing. So, no, I'm sorry, they're increasing. So by choosing the right endpoints here, we're actually getting what's probably a larger value than the actual. Okay, so this would be greater than. This is actually going to be greater than the actual value of the interval. And similarly, when we're using the left endpoints, because this is increasing, so it's an increasing function, then we're using left endpoints, we're choosing lower values. So this should be less than the exact value of the integral. And then finally, for the third part, we're going to use the midpoints, okay? So the midpoints are going to be the here, here, and here. So that's going to be 4, 6, and 8. Okay, so the midpoint is going to be f of 4, 2 times, again, you got the delta x there, f of 4 plus f of 6 plus f of 8. So f of 4 is negative 2.1, and then f of 6 is 0.3, and f of 8 is 1.5. And I get negative 0.6 for that one. So negative 0.6. Now, then we can't really say whether this is going to be greater than or less than or equal to the exact value of the integral. You can't really tell from here. That kind of depends on a lot of other values. Okay. Okay, so that's number 2. Let's go to number 3. And again, I messed this up. I should have put that in there. Okay, express the limit as a definite integral of the given interval. Okay, so you have this right here, and you want to figure out what's going on. Okay, so now we compare the delta x with there's a delta x there too, so that's really convenient. So they're there. So they're there. So now we just have to look and think about the rest of it. And you got the limit here. That's the same as that. The summation signs are the same. And so then this part right here is just going to be, your function is just going to be, just replace the xi stars with x's. And that's your function. And then here, this is the interval. So 1 to 3, and so 3 goes there. Okay, so yeah, this 3 goes right here. And notice that the 1 is right here as well. Okay, so that's the answer to that one. Let's look at number 4. We have a limit here. If f is integrable, then the integral is this. And this is using the right endpoints. This is right endpoints. And we're going to use all this stuff, and we're going to actually evaluate an integral. Now, in the future, you're going to find a much easier way we're going to show you a much easier way to do this, like a shortcut way to do it. But let's just work with all this information here to do it. Okay, so this is going to be the limit as n goes to infinity of summation. I'm just copying this down. Equals 1 to n, f of xi. Okay, now let me figure out what to put here first, okay? So, we'll figure out delta x first, okay? So let me come over here and do delta x. So delta x, that's going to be b minus a over n. B is 6, a is 1, so it's going to be 5 over n. That's our delta x. Now, x sub I is a plus I delta x. A is 1, and delta x is this. So it's 1 plus 5i over n. So that's what these are. Okay, now, just so we're not completely confused, I'll copy this all the way down. Now, this will go, actually, you know what? I will do this, okay? I'll do this to make it We know what f of x is. Okay, this is f of x, right? So right here, I'm going to put xi squared minus, wait. I'm just going to replace all these x's with xi's. Okay, and then I'll put a delta x here. And, well, I can't just write this stuff down. This is xi. Okay, now, we know that this is our xi, so we're going to put that there and here, okay? Okay, so this xi gets replaced with that. So that becomes 1 plus 5i over n quantity squared. This xi gets replaced with that also. And then this is a plus 4 there. Okay, so that's all that. And this, oops, need a different color. Okay, this 5 over n is going to replace that. And so we'll have a 5 over n on the end, like that. So all of this is multiplied by 5 over n. Okay, let's go ahead and try to simplify this. Okay, so expand all that out, and we get 1 plus, what is it, 10i over n plus 25i squared over n squared. And then here we have minus 4 minus 20i over n, and then plus 4. And that's all multiplied by 5 over n. Okay, so now these 4s are going to cancel, yay. And what else happens? What else do we got? Dang, I can't believe I botched this so badly. Okay, so this is limit. As n goes to infinity, goes 1 to n. Okay, so we have, let's do this. Okay, so we have a 1 here times 5 over n. So we'll just call it a 5 over, we'll call it 5 over n, okay? Now we have this piece and this piece. That adds up to negative 10i over n, times that is going to be minus 50i over n. Okay, then we have this times that. Oh wait, n squared. I'm sorry, n squared. Because there's an n here and an n there, so that's n squared. So 50i over n squared. Okay, then here we have 25 times 5, that's 125 I squared over n cubed, like that. Okay, there. So I combine everything and I distributed the 5 over n inside. Okay, now what I'm going to do now is I'm going to split it up into different pieces. So here, I'm going to rearrange it a bit. I'm going to factor out, so this right here is actually the sum of this minus the sum of that plus the sum of that. Okay, so, but then I can factor this part out and just have a 1 inside. Okay, then I can factor this part out I can't take the I out though. Because the I varies under here. The I goes from one, that's what the variation is. Okay, but I can take all that out. Okay, now now you see that we have these convenient formulas here. So we have this right here, which would correspond to that. And so this is just going to be n. Okay, and then we have this formula here, which is this one. It would correspond to that. Okay. So this just becomes this. Like that. So these are multiplied together though. These are multiplied together. And then we also have this formula here, which corresponds to this last piece. Okay, so this is all that. Okay, so we don't have very much space left, so that means I got to wrap this up really, really quickly. For this one, these are going to cancel. These are going to cancel here, and this is going to reduce that to 2 of these. And that, okay, so we get some cancellation. This first piece is just a 5, so that's just going to be 5. Okay, this second piece, as n goes to infinity, this and this are going to, this goes to 1 as n goes to infinity. So we get minus 50 over 2. Okay, likewise, all of this, if you expand this out, your leading term is going to be 2n squared. This is an n squared. So as n goes to infinity, that is going to go to 2. Okay? So this last piece, you're going to have 125 times 2 all over 6. And then, of course, these will reduce to 3. Okay? So in the end, you're going to get 65 over 3 as the answer. Okay. So let's move on to number 5. Express the integral as a limit of Riemann sums using right endpoints. So this is the formula for right endpoints. Do not evaluate. Okay, so A is 3 and B is 5, and then here's our and there's our function right here, the square root of 3 plus x squared. So that means that delta x will be B minus A all over n. So that's going to be 2 over n is our delta x. Essentially, what they want you to do is write this right here. They want you to like put it in this form, but do all the substitutions. And So you know the delta, the 2 over n goes in for delta x, okay? And f of xi, that's going to be this right here, the square root of 3 plus xi squared. Okay, but we're not quite done yet. Xi is going to be, is a plus I delta x. A is 3, and delta x is 2 over n. Okay, so that's 3 plus 2i over n. And that's going to go in there for that delta I right there. Let's put the 2 over n out front. And again, this 3 plus 2i over n goes in here. It's all squared. It's that whole xi is squared right there. Again, I forgot to put the, I keep on doing it. I keep on forgetting to put this summation sign. Okay, so that's what it should look like right there. That will be the answer right here. This will be the answer. Because they have this part already for you there on Webassign. This is what the other part should look like. And that looks like a lot of fun to do, or it looks like impossible to do effectively. Okay, so now let's do number 6, because that looks like a lot of fun. Okay, so the graph of G consists of 2 straight lines and a semicircle. So this part's a semicircle right here. And these are lines. Okay, so evaluate each integral by interpreting it in terms of areas. So the integral from 0 to 10, this is from 0 to 10. So A is going to go from 0 to 10. So we just want this area here then, is what we want. And we know for a triangle, the area is 1/2 the base times the height. And we know that the base is 10 and the height is 20. So that means that that's going to be 10, 1/2 10 times 20, which is going to work out to 100. Okay, so that would be the answer to the first part. Okay, now the answer to the second part. From 10 to 20, no, from 10 to 30. So from here to here, I want to know what's the integral from here to here. And we know that the area, okay, so a circle area is pi r squared, but a semicircle, which is half a circle, your area is going to be 1/2 of that. Okay, and this is under, so it's going to be negative 1/2 pi r squared. And r is 10, because from here to here is 10. From the center to there is also 10, and the center to there is also 10. So the radius is 10. That's going to be negative 50 pi. Okay, and then the last part, from 0 to 35. So you want to go from 0 to 35. Okay, so let's just calculate this last little area. Here are the bases. This is 30, so the base is 5, and this goes up by, this is also 5. $25 over 2. So the total area is going to be the area of this first piece, which is 100, minus this area here, plus the area of the little triangle right here. Little triangle. This area is 25 over 2. Okay, so that turns out to be 225 over 2 minus 50 pi. Okay, because this is 200 over 2, right? 200 plus 25 is 225 all over 2, and then minus 50 pi. So or this one right here. Okay, great. Number 7. Evaluate this interval by interpreting it in terms of areas. Okay, so for this one, what we're going to look at is y equals 1/3 x minus 2. And we're going from 0 to 9. Now, when you're at 0, this has the y-intercept -2, so you're down here at -2. And when you're at 9, so let's see, f of 0 is -2, f of 9 is 1/3 times 9 minus 2, which is going to be 3, which is 1. Which is 1. Okay, so the curve is going to look like this, or it's going to be a line segment. It looks like this, something like that. And let's figure out where it passes here. So if we to find this point here, we take 3rd x minus 2. We set that equal to 0. So 1/3 x equals 2. X is 6. Okay, so that's going to be 6. Okay, now the integral will be, if we call this area 1 right here, and then call this area 2. Okay, that's area 1, this is area 2. The integral is going to be equal to negative area 1 plus area 2, because this is under the x-axis, right? This is under the x-axis, so that's negative area. So count it negative. And this is above the x-axis, so that's positive. Okay, now this one, this area here, it's 1/2 the base times the height. The base is, from here to here is 6, and this is 2. So 1/2 times 6 times 2 is going to be 6. Okay, so that's going to be -6. And then this other area here, the base is 3, the height is 1. So area 2 will be 1/2 3 times 1, which will be 3/2. Okay, so that will be plus 3/2. Okay, so that's -12/2 plus 3/2, which gives you -9/2. And that's going to be the answer. Again, in the near future, we'll show you a kind of an easier way to do this using the fundamental theorem of calculus. Okay. Yeah, theorem that's lots of fun. The fundamental theorem of calculus. Okay, so number 8. So given that this integral is, and they get this by using the fundamental theorem of calculus, by the way. Or that's one way to get this integral. You could also do it using the definition. But this is b squared minus a squared over 2. From 0 to pi of cosine x is 1. So that's kind of interesting. And then you're supposed to evaluate this. Okay, now there's a bunch of properties of integrals which I haven't emphasized, but essentially, here, let me just explain it right here. So, okay, so integral property. If you integrating from a to b, which gives be anything. So here, in this case, a is 0 and b is pi over 2. And you have a constant times the first function plus another constant times the second function. Okay, then this is the same as C1 times the integral from a to b of your first function plus C2 from a times the integral from a to b of your second function. Okay, so constants, so sums can be split up into 2 integrals. Constants can be taken out. Okay, now there is one case where this doesn't work. There's definitely one case where this doesn't work. It's where this sum has some like canceling going on, which makes it so it's integrable, where if you're just taking these by themselves, they're not integrable. So, but this is going to be true if the integrals on the right-hand side exist, both of them. If both these integrals exist, then this is going to be true. Okay, if not, because you could have the situation where this side works, but that doesn't, because these things cancel each other out. Okay, but we're not going to worry too much about that. Okay, so here's what we have then, and we apply that property to this. That means that we can take the 2 all the way out. Maybe what I should do is like do more steps. Okay, let me do more steps. I can split it up into 2 integrals, like that. So we're integrating this one right here, plus the integral of this negative 7x, right there. Okay, then I can pull the constants out. You can't pull functions out, by the way. That gets into lots of trouble. Okay, but you can, so you can't pull the x out. Oops. So I was just showing you what you can't do. This x has to stay in there. Okay, now they said that this is 1. Okay, so that is going to be 1. And you have this right here. The integral from a to b of x dx. X dx is going to be this. And so you have pi over 2 squared. That's b squared. So b is the upper limit. That's pi over 2 minus a squared and that's all divided by 2. Okay, this is a 2. This becomes, what's this become? 7 pi squared over, this is like 4, and then that's going to make it 8. And it's 7 pi squared over 8. Okay, so that should be the answer right there.